Hello, hello. We are back. This is a quick stream. Um, we're just streaming some things, trying to get some clarity. I don't know. This whole power business can be a little confusing, especially if it's not explained properly. So we just need to understand it a little bit more. So what happens is, it turns out, the way I approach this is that whenever we conduct a hypothesis test, it is not 100% guarantee that our results will hold true. So in other words, if we have here, let me get this out. A basic example. So let's say our null hypothesis is 0, and our alternative hypothesis is 1. And what we do is assume true and try to show, if possible, actually we should say so here's our statements, our null hypothesis, alternative hypothesis. According to this diagram, so this setup is related to this diagram. All right. So here is the distribution of values of z. Remember now, z is it's a factor of the standard deviations away from the mean. So if we know that the standard deviation is 1, if our mean is standard at 0, it's just the standardized normal distribution, then our z values will be the distance it is away from the mean. So here, it says here, here's the distribution of values of z when the hypothesis tested. The mean is 0, and we suppose that it's true. Alpha is the probability of rejecting the hypothesis tested when the hypothesis is true. So in other words, in this region, this is like the critical region. It is this region where we set our alpha barrier. Now, 0.05 on a standardized scale is a little bit less than 2 deviations away from the mean. All right, so this is 5%. The bottom half is 95%. So this is about 1.7 something. Now what happens is we draw another sampling distribution mean, but we do it underneath, because if we put it in there right now, it would look too confusing. There's too many lines. So we'll put it directly underneath, but the values are still matched up accordingly. This time though, our sample mean is 1. All right? And so that means that right at 1, we have the average. That's the mean. So since here is the distribution of values of z, when a particular alternative hypothesis means z equals 1 is true. And so what happens is we create this line here. And as you can see, beta is represented by the shaded region, it is the probability of accepting the hypothesis tested when the alternative hypothesis is true. And then 1 minus beta, which is called the power. Power is the probability of rejecting the hypothesis tested when the alternative hypothesis is true. All right? And so, as you can see, as this shifts further and further away from the mean, the beta gets smaller and smaller, and the power gets bigger and bigger, and vice versa. So it's kind of I guess this is a good illustration of what's happening. If we click on the slides, see if I can pull up the slides here. Hypothesis testing errors. Type 1 error, the probability that we reject H null when H null is actually true. So for example, let's say that it is true that, it really turns out to be that the mean is really 0. We assume that it's true, but what if it is really true? There's still a chance that we sample something and our sample just happens to be in this region, right? And then if we were to reject it and say, you know what, I'm going to accept the alternative because my p-value, which is the probability value of being in this region, is less than 0.05, I'll reject the null. But the fact of the matter is the null could be true. So we can set the probability, which is equal to alpha, of the type 1 error at a level we choose. And this is because if our alpha level is too high, like if alpha was set to 10%, we could get a type 1 error because if our p-value is like 6%, it's less than alpha. Are we just going to reject the null at that point? Theoretically, we can. Sometimes that's why it's best to set our alpha level at 1%. The problem with setting it so small, though, is that we can end up getting the type 2 error. And so the challenge is figuring out the right sample size so that if we do set it at 5%, we can dictate what our power could be so that we can be more confident in rejecting or accepting the null, or failing to reject the null. The challenge is that as we lower the probability of a type 1 error, we increase the probability of a type 2 error. It's inverse. Our choice of sample size n affects how we balance type 1 and type 2 errors. And so here's that slide. What we see is that there's two things going on. If the null is true, there's two possibilities that can happen. Either we fail to reject the null, which would be the correct decision, or we reject the null, which would be the wrong decision, and that's a type 1 error. And the reason why we've rejected the null is probably because our significance level was too high, or our sampling test was turned out to be too low. And then the opposite. What if the null really is false? Now, if the null is really false, we should reject the null in our hypothesis test, which would be a correct decision. But sometimes, though, the null could be false, and we do the testing, and it turns out that we fail to reject the null. And so this is considered a type 2 error. And to actually calculate that, like if we were to have As you can see, um, because our mean was actually one deviation away, the chances of getting a correct decision is about 26% chance in here. So it's a pretty good chance. Um, but there's still doubt. But it all depends now if the null in actuality is false in the first place. So here's what I'm going to do. Um, suppose we have, like I said, a basketball. I'm going to put all this. So the basketball's claim is, hey, I'm a. Let's see if we can. Trying to make it a little bigger. Uh, we'll just stick with this. So what I have here is that let's assume that our null mean is 89. The testing mean that we tested was 85. We don't know the standard deviation, but we want our power to be at 0.8, and the sample size was 20. So let's run a test on this. So what did that give us? Oh, it's two-sided. Alpha set at 0.5. Let's go back. Let's see if that would have changed anything. Standard deviation now is 0.06. And let's do sides 1. Let's run it. So this time I actually know my power. I mean, I don't know my power, but I do know a standard deviation this time. So let's see what happens if we want to calculate the power. This is good. I'd get an 80% power based on this, which is what we would expect. Let's say we want a 90% power, and we don't know how many we need to sample. So to actually get a 90% power, we'd have to sample 28. So the guy would have to take 28 shots, the basketball player. All right, I hope this was helpful. We're going to end it here. It's just a quick little video going over some of the important facts about type 1 errors, type 2 errors, and how do we, why it matters, why our sample size matters when we're dealing with normal distributions. Um, Even though, especially if we don't know the t-value, we will the degrees of freedom changes the Bell shape, and it's an approximation. So in order for our hypothesis test to really work well, we have to be careful and mindful of our significance level as well as our sample size. So these are the two things that we really need to focus in on, um, the alpha level and the sample size. There's also the effect size, and we need to really study that. We need to understand that again. The effect size can be different things. So we'll definitely discuss that as well, probably sometime in the future. This is really helpful. It's good to actually study these, because we learn the little details as we discuss these things, and I really encourage feedback as well as others, um, taking the lead on this, and really uh, talking about the different things that have popped up in the classes. All right, over and out. Have a great day.